what is the Earth's magnetic field in this room? Half a Gauss. Gauss is 10 to the minus 4 Tesla, so it's 100 times weaker. Okay, the field due to this little current at this point, 1 inch away, is 100. So a 10 amp current, okay, but it's just this element. So if you wanted to, okay. For part B, there's r hat. We have to find the angle. So this angle is equal to this angle. Okay. Tan theta is 3/4. So sine theta is what we'll need, is 3/5. Okay. Tan theta is 3/4. Sine theta is 3/5. Okay. So ds cross r hat, magnitude is ds sine theta equal to ds times 3/5. So the expression is dB is mu naught 4 pi I ds cos r hat r squared. So the magnitude dB is just the magnitude of this is that. Divided by r squared. ds is 0.5 millimeter and r is 5 centimeters. So you can calculate that. Will it work out bigger than this or smaller than this? Smaller, you're further away. And then, and the sine theta is also smaller than 1. So as you go in this direction, okay, so $1 if you answer this. Well, okay, maybe not. Well, in the limit, what is the asymptotic value on that line? 0. Along the axis, it's 0. So as you're going there, you're coming close to 0. But also, here's the simple thing: as you're going further and further, r is going to infinity. That's it. So there's two factors. R is going to 0. R squared is going to 1 over r squared is going to 0, and sine of 0 is going to 0 as well. Because as you're going further out, the angle is getting smaller and smaller. And the angle theta is tending to 0, and that's also tending to 0. Okay.
Go back to the other page. Thank you.
All right, before we start solve the next problem, this element of the current, what is the magnetic field it's producing over there? So this element of the current, what is the magnetic field it produces here?
0.
0. Okay, so you're not producing any magnetic field along the line you're traveling, along the line in which the line travels, the charges travel. Okay, so if you have a wire like this carrying a current, in this problem you want to find the field there. So you see, this element is not producing a field there. This element is not producing a field there. Only this element and this element produces a field. Okay. This element, okay, so this is part of a circular arc, and remember the field it produces is, you point your fingers like that along the direction of the current. This guy produces a field coming out of the sheet, and this guy produces a field going into the sheet. And because this guy is further away from him than this guy produces a stronger field than this guy. Okay, so the net field will be coming out of the sheet. Okay, so you have to remember all of that. Okay, let me calculate. So we'll call this 1, 2, 3, 4. Field due to 1 and equal to field due to 3 equal to 0. Now let's calculate field due to 2. You guys understand the notation? Okay. All right, so we'll call this ds. Here's r hat. Okay. So field dB2 okay. So here is ds, here's r. ds cross r hat, if you turn a screw this way, it's coming out of the sheet. So that gives you the direction, which we already told you using this right-hand rule, okay? You point your fingers in the direction of the current and the thumb points in the direction of the field. So the field is coming out. Okay, what is the magnitude of ds? You see they're perpendicular to each other. It's ds r sine 90. R hat, magnitude of r hat is 1, so it's just ds. Okay. All right, so dB2 due to that small element is mu naught 4 pi I ds over r squared. What is r? The distance, it's just a. So it's a squared. So B2 is dB2 sum of, and you see mu naught I 4 pi a square sum of ds. What is the sum of all these arcs? It's a quarter of a circumference. A quarter of 2 pi a. So what I'm going to do is write it as 1 over 4 mu naught I 2a. So the field due to this arc is mu naught I 2a, a quarter of that. So if this was a full circle, the field due to that full circle at the center would be just this guy. Yeah. What is the field due to this guy? The radius is b, so the same expression except the radius would be, except that that point is pointing into the sheet. Okay, so the net field is 1/4 mu naught I over 2a minus 1/4 mu naught I 2b. Okay. That's the net field. And it's coming out of the sheet of the paper. Again, notice, really all these problems are about doing this integral, the impossible integral, and we're doing it only in very special cases where where there's symmetry involved and you're just adding up arc lengths and stuff. Okay. So for instance, if this guy were not in a single plane, if this were bent, had a slight kink to it, this problem would be impossible to do. The magnitude of the magnetic field 50 centimeters from a long thin straight wire is 8 microtesla. So this is roughly 1/10 of the Earth's magnetic field. What is the current through the long wire? So in a wire like that, you saw that the magnetic field is concentric circles like that, and at a distance r, magnetic field is given by mu naught 2 pi r, mu naught I, or is there a 2 pi?
It is 2 pi.
Hmm?
It is 2 pi.
Yeah, okay, it is 2 pi. Okay. What is the current through the long wires? So they give us the magnetic field, they give us the distance, so we calculate the current. Eight microtesla, 2 pi, 50 centimeters, 0.5 meters. The Tesla cancels, the meter cancels, and you get the ampere on top. So that'll make that 2, 5, 8 times 5 divided by 2. No, 8 times 2 pi times 5. Oh no. So 20 amperes. So a 20 ampere current is half a meter away, is producing a field 1/10 the Earth's magnetic field. Yeah. Here's a 20 ampere current again. A long straight horizontal wire carries a left to right current of 20 amperes. If the wire is placed in a uniform magnetic field of magnitude 4 times 10 to the minus 5 Tesla, okay, so that's the Earth's magnetic field that is directed vertically downward. So here's a magnetic field that's vertically downward. And where on Earth will the field be? Okay, what is the direction of the magnetic field in this room? It's horizontal, parallel to the ground. Is there anywhere where the Earth's magnetic field will point toward the Earth? The poles, near the poles it'll fall. Okay. So you're near the pole. Okay. And this is actually near the magnetic pole, which is not the same as which is not the same point as the geographic poles. Anyway. So this guy, okay, so what is the resultant magnitude of the magnetic field 20 centimeters above the wire, 20 centimeters below the wire? We'll calculate it 20 centimeters below the wire. Below the wire will produce a magnetic field like that. Remember, you stick your fingers out and it's into the sheet. So this is producing, the wire is producing a magnetic field there. There's the Earth's magnetic field. And so the net field will be in that direction, okay? And now I'll draw this a side view. Here is the magnetic field produced by the wire. There's R. And here is the Earth's magnetic field. And this will be the net field. The field produced by the wire is, we just saw, we have the expression mu naught I by 2 pi r. Let's calculate that. The current is 20 amp. So B from the wire is, you get 2, and this is 10 to the minus 6 and 2, that cancels 2, so 20 times 10 minus. So the field produced by the wire is stronger than the Earth's magnetic field. Okay. So if this wire were pointing north-south, this magnetic field would be pointing east-west. I mean, it would be pointing west if this were pointing north. Okay, so this is 20 Tesla, this is, I mean, microtesla, this is 4 microtesla. So the net field, the magnitude of the net field is square root of 20 square plus 4 square. If you want, you can calculate the angle theta. Theta is tan inverse of 4 over 20. 11.3 degrees. So this field is 11 point, this angle is 11.3 degrees below the horizontal. Two long straight wires are parallel and 10 centimeters apart. One carries a current of 2 amperes and the other carries a current of 5 amperes. If the two currents flow in the opposite direction, what is it, a repulsive or attractive force? It's a repulsive force. Every time it's 50 cents, but it's not quite getting to $1.
One day.
Yeah, we should just add up all. If the magnitude and the direction of force per unit length of one wire, okay. Okay, so the force, if the currents are in the same direction, the force is attractive, and if they're in the opposite direction, the force is repulsive. And again, this formula works only when the entire things are parallel to each other. It won't work like that if they're skewed. The force per unit length only works like that. Yeah. So the force is tiny for fairly decent sized currents. Okay, so these two wires are carrying 2 and 5 ampere current. They're that far apart, and the force is for every meter, a meter is this long, the force is only a micronewton. So the force between the wires is small.
Could you go back to that slide?
You go back to the other one too.
A flat circular loop has 20 turns. The radius of the loop is 10 centimeters. And the current through the wire is 0.5 ampere. Determine the magnitude of the magnetic field at the center of the loop. Okay, we have an expression for the magnetic field along the axes. Okay, and here's the expression. So along the axis, here is the expression. Okay. And you're finding at the center of the loop, so z is 0. Okay, so r square 3/2 will be, this would be r cubed, and r square cancels, so mu naught n, I'll write down this expression and put z equal to 0. Twenty turns. The current is 0.5 amp. 2 times 0.1 milliamp. That's 10 to the minus 6. 2 pi times 20 times 0.5. 20 pi microtesla. Two flat circular coils, each with a radius r and wound with n turns, are mounted along the same axes, so they are parallel a distance d apart. So this problem is on the exam. What is the magnetic field at the midpoint? Okay, so we'll call this loop 1, loop 2. What does loop 1 produce at this point? What is the direction of the field that loop 1 produces? So wrap your fingers around there, and the field is like that. So B1 is in this direction, and loop 2 also produces a field in that direction if the currents are, okay? So you see this device, you can use this to measure currents, in the sense that, okay, if you have a known current, and if you pass a equal current in the opposite direction, the net field at this point in the midpoint should be 0, because this magnetic field and they're in the opposite direction, okay? And it's the same expression that we're using. Okay, so R is what is Z?
The distance from
Mhm.
the mid-
So for the loop 1, Z is minus D by 2. For loop 2, it's plus D by 2.
So you said normally the fields are gonna be going in opposite directions and they're gonna cancel each other out.
If the currents are in the opposite direction.
Why are the currents in the same direction? Because they're parallel?
Yeah, do for
Parallel. So if they were.
current flow in the same direction.
Oh, okay, it's just saying, that. Okay,
Mhm.
cool.
So that's the net magnetic field at that point.
So how would that be an exam question? Because usually the exam questions are numbers, or are you just gonna give values for the things to put into that equation at the end?
In the formula sheet, I'll be giving you this formula.
Okay.
A superconducting wire of diameter 0.25 centimeters carries a current of 1,000 amps. What is the magnetic field just outside the wire? So you saw that. Uh, so if that's the current, the magnetic field, again, stick it. So the dot means the current is coming out. We are doing a cross section, and the magnetic field is like that. And just outside the wire, the magnetic field is, if R is the radius of the wire, the magnetic field is mu naught I 2 pi R. A 1,000 amp is quite a large current. So this is 10 to the minus 4, 10 to the minus 1. So 2 times 0.1 divided by 0.25. Okay. So 8/10 of a Tesla, which is a fairly large magnetic field. So if this, the wire is about this thick, it's carrying a 1,000 amp current. And right on the surface, it's 8/10 of a Tesla.
Professor,
Mhm.
is this supposed to be the diameter on the bottom? Or the radius of it, of the wire itself?
It's just twice 16 and 1.6 Tesla. No. If a current is 2 amp, how many turns per centimeters would be wound on a solenoid in order to produce a magnetic field of 2 millitesla within it? Okay, so again, a solenoid is tightly wound wires, and the magnetic field inside, is given by mu naught Ni. N is the number of turns per meter, okay, in SI units. So that's 10 minus 4, that comes to the top. That's the 2 cancels, so it's 10 to the 4 divided by 4 pi. And what you're left with is a per meter. The ampere cancels, the Tesla cancels.
If you find that answer, can you go back to 33, or sorry, not 33, 39?
Mm-hmm.
I have a question.
Turns per meter, and 1 meter is 100 centimeters, so 7.96 turns per centimeter. So here's a centimeter. Every centimeter of the wire has 8 turns of wire. That's a centimeter. And if you want to produce a uniform field in this room, the cylinder has to be this big, and you just wrap the wire around it.
At 39. So you said that z is equal to d over 2, so therefore z squared is d squared over 4.
Mm-hmm.
So what I'm confused about is down at the B net equation at the bottom,
Mhm.
why you didn't replace z squared with d squared over 4. Because you have z squared plus d squared over 4. Shouldn't that be r squared instead of a z down there? Or am I?
Mhm. A toroid has 250 turns of wire. So here's a donut, and we're wrapping wires around it. So the current here is going, and let's say the current is flowing like that. Current here is flowing in, and the current here is coming up. Its inner and outer radii are 8 and 9 centimeters. So inner radii is 8 centimeters, outer radii is 9 centimeters. What are the values of its magnetic field at R equal to 8.1, 8.5, and 8.9 centimeters? Okay, what they're asking is, again, if you wrap your fingers around like this, the magnetic field is in this direction. Okay? Okay. And you can, I mean, from symmetry, you can see that it's plausible that the magnetic field at a given radius is constant, the magnitude is constant. I mean, so it's tangent to that thing. The further out you go from the center, the weaker the magnetic field gets. Okay? So here's Ampere's law. Ampere's law says B dot ds, the line integral, is equal to mu naught times the current going through that loop. And again, if what are the rules? If you're taking the line integral along in this sense, this current is positive. Okay. So we'll take the line integral along this. And what is this line integral? Well, the magnetic field is constant. So we'll allow B dot ds, they're parallel, B and dot ds. B dot ds is equal to B ds. And so that integral is just B times 2 pi r. That's equal to mu naught times the current, mu naught times the current inside the loop. What is the current inside the loop?
20 amps.
Okay, so the current inside the loop is 20 amps times every winding, that's 20 amps, 20 amps, 20 amps coming out. So 250 times 20 amps. Okay. So here's a situation where this Ampere's law was useful in calculating the magnetic field in very symmetric situations. And again, you do this integral where you can just essentially write down the answer. See, the value of this integral was just that. Okay, so if you want to find the field at this point, you put r equal to 8.1 centimeters. You want to find it at this point, you put r equal to 8.5 centimeters and 8.9 centimeters. So let's do 1. So you see, as you increase n, you can make the field stronger and stronger. And And that's what this is, see? There, so there's the donut wrapped around with wire, and you're producing that magnetic field inside. And so the plasma can be trapped around there. See, the plasma, which is at 2 billion degrees, is not even touching the walls. Okay, well, maybe it's not at 2 billion, but whatever, it's pretty warm. Okay, that makes that 10 to the minus 5. We'll make that 10 to the minus 3. So 2 into 2.5 into 20 into 10 minus 3. So 12.3 millitesla. About 100 times greater than the Earth's magnetic field. Okay.